This is my fourth video in simplifying trig expressions using fundamental trig identities, and in this video we're going to deal with a situation in which we have some complex fractions, as well as in terms of what we're doing with these two fractions, we're adding them together. And recall that when you add two fractions together, we need a common denominator. Okay, so we have this expression here: sine x over 1 plus the cosine of x, all in the basement here, this binomial, plus cosine x over sine of x. Okay. So in terms of dealing with something like this, let's remember when you are adding two fractions together and you need a common denominator, that is, if we were to have like a over b, I suppose plus or minus could be a difference, c over d, we would say that first of all that the common denominator would be the product of the two denominators. Okay, so we would say that if I wanted to find a common denominator here, we could take everything on the left here times d over d, and we take everything on the right here times b, and what you end up with is a common denominator that is bd. And so we would end up with this. We would say everything is over bd now because they have a common denominator. And on the left side we would say that just we have a times d, which by the way d is this denominator that was on the right. And then we say plus or minus, depending upon what you had here in the first place, c times b, or we could list this as bc. So the overall value of this would basically, if you had to, go through a quick explanation of this for somebody else, we say, well, what would the value of this be? Well, we would say 3 times 5 would be our common denominator. That's our b times d. And then in terms of what we get overall, we could say, well, 5 times 2 is 10, and then 1 times 3 is 3. So I would get overall, I would get 13/15. And what this does is it just allows us to kind of bypass all of this extra work that we would have had to do in this first place, okay, to arrive at this conclusion. So when we talk about algebraic expressions over here, that's exactly what we're going to do, okay? So we have sine of x. I'm going to rewrite this so I have a little bit more space to work with here. We're going to say sine of x, and this is over 1 plus the cosine of x. And we're taking that entire fraction and we're going to add it to the cosine of x all over the sine of x, okay? And so in terms of what our common denominator is, again, recall that the common denominator in an algebraic sense here will be the product of these two denominators. So what we end up with here is this: we essentially have to take everything on the left over here. We're going to take it times a sine x over sine x. And we're going to take everything on the right over here. Now this is the important part, times the entire denominator from the left, which is entirely 1 plus cosine in parentheses, 1 plus cosine of x. Okay, so what we end up with here is this. I'm going to write a long drawn out expression here, but the common denominator is going to be what we get when we take the sine of x times 1 plus the cosine of x. This was of course our common denominator. We could have just said that instantly off the bat, knowing what we know about adding and subtracting fractions. But we say up here on the top left, we say sine times sine. What we end up with there is, well, sine times sine is sine squared of x. And we say, okay, so we had plus, and then we say cosine times 1 plus cosine. So we say cosine x times 1 plus the cosine of x. Now, I have got some sage advice for you all that are viewing this right now, but it's going to be this. In terms of the denominator, what I want us to do is leave the denominator factored. So, I might be inclined to distribute this through here, but we're going to leave the denominator factored. Okay, we don't want to unfactor it because we're going to get some things to cancel here. Now, as far as the numerator is concerned, I say go to town. As a matter of fact, you may feel free to distribute this cosine of x up top here. So now, writing out what we have, we say, well, then I have the sine squared of x on top, plus now cosine times 1 would be cosine of x. Now plus cosine times cosine, which is a cosine squared of x. And this is all over sine of x times 1 plus the cosine of x, where we had not distributed this. Okay. So what is so nice about this expression here is the fact that on the top here, remember, addition is commutative. We can do it in any order that we want. So essentially, I could say, well, we have sine squared of x plus cosine squared of x. That's the same thing as sine squared of x plus cosine squared of x plus cosine of x. And the reason why I mention this is because, remember, with our Pythagorean identities, sine squared of x plus cosine squared of x equals 1. So if I were to rewrite this for those of us that like to see things in a nice, neat order, I'm saying that this sine squared of x plus cosine squared of x plus cosine x, we could rearrange the top so that now it looks like this. We say, well, then I have sine x times 1 plus the cosine of x. What I know about this is essentially that this sine squared plus cosine squared right here, we can cross this out and we can say that that's the same thing as 1. So now what this leads us to on the top is we have 1 plus this loose cosine of x over here, and this is over the sine of x times 1 plus the cosine of x. And the reason why I wanted to leave this factor in the first place is because, well, if we associate these two terms on top as being one complete value, I notice that we have this over something times something in the basement. Okay, and since this is a product down here, we can say that this factor in the bottom cancels out with this factor on the top, and what we get left with is this. We get 1 over the sine of x. And in terms of simplifying things, this is much simpler than what we started with, because this is simply just the cosecant of x. So to tell you this, it might make you a little bit frustrated, but we could say that the original expression up here could have been written as just the cosecant of x in the first place. We just had to find a common denominator, distribute, pull some substitutions here, and then some algebraic cancellation to arrive at the cosecant of x. Cheers.